Hey everybody, we're on problem number 3 for the review. We are looking at temperatures and daylight hours in two places, Barrow, Alaska and Jacksonville, Florida. Sorry, these are all in the United States. I wish I had some better data for outside the United States, but this is what I have. The first thing we're asked to do is use the table to create a scatter plot for months versus average daylight in Barrow, Alaska. So we're going to do months versus average daylight. So we're going to be using those two first. One thing you notice is I can't plot months, right? I can't plot January. There's no way for me to type that in when I go to my stat plot, right? So we actually need to convert our months to the number of the month, right? So this might be 1, 2, 3, 4, 5, so on and so forth, right? So those are the numbers we're going to put in for X is month, and then in this case Y is going to be daylight hours, all right? I'm going to pause it and put those numbers in. Okay, so I've entered these into list 1 and list 2. One thing you really want to pay attention to is your window, right? You want to think about what do my X values need to be. I don't need to go very negative, so I'm going to go from -1 because my lowest number here is 1. And my X max is, well, there's only 12 months in a year. I'm going to go a little bit past that and go to like 16 or something. Actually, let me go to 24 just because that's 2 years, right? So I'm going to go beyond what I need to go to here. For Y min, again, there's no negative temperatures here, but the lowest one is 0, so I'm going to go below 0 and say -10. And the highest temperature here looks like it's about 19. So let's go to, I don't know, 20 or 25. Let's go to 25, okay? So if we graph these, you're going to see this, right? And your first temptation might be, hey, that looks like a parabola, right? Like that totally looks like, you go up, you come down. But you want to think about it, like what's going to happen after December, right? After December, you go back to January, and you'd expect similar temperatures this January as you would from last January. And after January is February, right? And you would expect similar temperatures from this February as last February, right? So a parabola would say, if you chose a parabola, let me see if I can get this real quick. And just ignore those other lines on there. I forgot to delete those other functions. But if you're going to say this is a parabola, then you're saying this happens. And so you're saying next, I don't know, let's say this is July. You're saying the temperature is going to be way down here, negative something, right? So that doesn't make sense. What we expect to happen is that, okay, yes, it goes up and then down, and then we'd expect, it to repeat the next year and the next year and the next year. So what we should be thinking, because we know about temperatures or we know about daylight, right? You're not going to have negative hours of daylight in the future. And I was misinterpreting that because I was saying it was temperature, it's daylight. You're not going to have negative daylight. And so we should be thinking some sort of trig function, such as sine or cosine. And pretty much they're the same thing, just with like a horizontal shift. And so typically we focus on sine. So what we're going to do is we're going to try to use a sine function to describe this. So before we do it with the calculator, let's think about what we know about sine functions, right? We have y equals a sine b x minus h plus k. A is the amplitude, right? That's how far up and down it goes from the midline. So if I draw this midline here, that's the amplitude, and so is that, right? B is the period. It's always, whatever the period is always 360 over this B value. H is a horizontal shift, so we move it left, this whole thing left or right. We typically don't need to worry about that. And then our K value here is our midline. This is our midline, which is this number here. It's also the average of all these things. It'll always be the average of, if you added up all the points and divided by however many points you had, be the average. So knowing this, we should be able to figure out some of these things reasonably. Let's start with B. We know that B is the period, and it's 360. The period is always 360 over B. In this case, the period is 12 because there's 12 months in a year. So we know that 12 equals 360 over B, or 12B equals 360, or B equals 360 over 12. And just real quick, let's do 360 divided by 12. Second quit. 360. I should know this one already. I've done it a bunch of times. So we should know our B value should be about 30, right? That's where that B should be. And then from 30, we can kind of, without even using a calculator, we could say, okay, well, what's the farthest away we get from 30 in both directions? right? So look on here for the min. The min here is 0, which is 30 away from that, and the max here is the max here is 24. So I'm not sure I was able to do that on my window. I'm gonna go back to my window. I said 25, so I did have it covered. I'm gonna go a little bit bigger than that though. Right, and so that's pretty close to 30, but not quite 30. So my amplitude should be somewhere between 30 and 24. Let's actually average those out, and let's say 27. Right, so let's say our amplitude is going to be 27. And again, we're just kind of doing this without doing anything else, right? No, I'm sorry, that was dumb of me. That was using the midline as that. I was using the frequency as the midline. We don't know what this midline is yet, but we could kind of figure it out. So let's use the calculator real quick to do some of this other work for us. Actually, I think we can do a lot of this without the calculator, but we'll go to the calculator in a second. So we were on the right track, right? Our min temperature, our min number of hours is 0. Our max number of hours is 24. So if you think about what the average number of hours should be, the average number should be 12. That's going to be our 12, that K value. And then our amplitude should be half of that because, again, it's this distance, right? If this is 24 and this is 0, then the amplitude should get us up 12 and down 12. So we could write sine of 30x plus, and then this is going to be also 12. And let's just try that real quick. Let's actually just clear away all these other functions that I had in there from the last problem, and let's try 12 sine 30x plus 12. And there's one thing I need to do. I need to go to mode. I need to put my calculator in degrees. And then I'm going to graph, and you can see that it's really close, but it's off a little bit, right? You can see like it's if it were shifted over to the right, it would actually work really well. One thing I could try to do to fix that is I could make this a cosine and see if that helps at all. That did not help. Another thing I could try is I could put a negative number here. There, that one actually works, right? So you can like play around with things like that. That one actually works pretty well. So we could modify this, just by trial and error and be like, oh, this should be negative 12 cosine 30x plus 12. Let's see what the calculator does for us, right? So let's go to stat calc, and we're going to go to here, which is sine reg, right? It's going to give us a fit for our calculator using sine. It calculates. Oh, come on, what are you doing? And it's going to tell us that the model is y equals a value of 12.66 sine b value. So this b value is going to be deceptive. Let's use RB. Don't use this b because this is in radians, and in this course you don't need radians. So you're going to need to figure out the b value yourself. Or you can convert it. It always gives this in radians. So if you wanted to convert this to degrees, you would just multiply by 180 over pi. Let's try that real quick just to convince you after I write this. And then there's a c value, x minus negative 1.49, and the d value is 11.85. Okay, so I'm going to try to convince you oh, I didn't get it. Darn it. Stat calc sine reg. The b they give there is 0.496, right? So I'm going to go 0.496 times 180 divided by pi, and that's going to give us 28.4, which is pretty close to 30, right? So this is how you convert from radians to degrees, and that b value they always give you in radians, right? Okay, so we're back to this. I'm going to use 30 just because that's what we calculated using the months. So we could actually graph this one as well and just see how much, if it's a better fit or not. We're going to put 12.66 sine 30. Oh, they already had the parenthesis. 30 x plus 1.49 close plus 11.85. And you graph, and that does not look like right at all. So what did we do wrong? Let's see. Sine 30, 1.49. Let's see, what did we do wrong? No, stat calc sine reg. Did I write one of these down wrong? Oh, I see. See, the format they put in is bx plus c, so I actually don't need that parenthesis in this case. When I write it, they're just saying their b value does not. Their c value does not include the distribution, so they're just writing it like that without that extra set of parentheses. Let's see if that works better. There's the cosine one that we came up with by hand. Hurry up. Still not working. Okay, let me pause and figure it out. Oh yeah, so it's bx plus c, so this would actually be, there wasn't a minus there in the first place. That would actually be a minus sign. Sorry for the confusion on that one. Just look at what the formula gives you, and I was assuming it was like some other formulas that we had that have a minus instead of a plus there. But this calculator has a plus c, not a minus c. And it's still no good. Did I fix it? Okay, I know what it is also. This is also in radians. That c value is also in radians. So we're going to take that value, 1.49, and we're going to multiply it by pi, 180 over pi. Oh, come on. 180 over pi. No, not 9. And we get 85.37. Okay, so we're going to go back in here and we're going to change this to 85.37. It's better. What's some better work? As you can see, sometimes just doing it by hand is easier than using the calculator, especially if we're not dealing in radians. Now what? Now I'm probably missing a parenthesis. Let's see. Yep, missing a parenthesis. One last time. There she is. You can see the model the calculator came up with is just about as good as the model we came up with without doing anything, right? Okay, so again, that number would be a little bit different. Let's use our model. I like our model better, right? Because we came up with it just by knowing some things. So the model that we're going to use is this one, right? Negative 12 cosine 30x plus 12. Domain and range. Domain in this case is the x values, which are the months. This is going to be all whole numbers. Yeah, all real numbers. Right, you can plug in 1, 2, you can plug in 1.5, which would be like January, middle of January. 5.75 would be like towards the end of May. Right, so you can plug in pretty much anything. The range is the y values, which in this case are the daylight hours. Daylight hours should not go below 0 and should not go above 24, right? Because if you do, you got a problem. You're not on Earth anymore. Next, find the average annual temperature. Find the average annual temperature in Barrow, Alaska. What is the significance of this number in the graph of your model? Ooh. Okay, you're not going to see annual temperature, average daylight hours, average daylight in the year, over 1 year. All right, so I'm kind of changing this, but you'll see this one instead. So we're going to find the average of all these numbers. We kind of already talked about what this is, but let's just do it real quick. We're going to add all these together and divide by 12, right? So 0, let me pause and do it so you don't have to watch me do it. Actually, I want to show you something. So I don't need to actually do this by hand and add all these up together, right? What I'm going to do is I'm going to press Stat, Calc. I'm just going to do one variable statistics. I'm not on list 1 because my temperatures were in list 2, so I'm going to press second, and then number 2 down here is list 2 in blue. I'm going to press calculate. It's going to do all of what I need it for me, right? So the X bar is 12.5, right? So X bar, the average daylight is 12.5. What's the significance of this graph in the terms of your model? Well, that is our midline. The average temperature is the midline, right? So that's, you don't really see it exactly on there, but this is a way you could have actually had a different answer for your midline down here, or in this equation you could have put 12.5 there instead, because that is the average temperature. Find and explain the meaning with the context of the problem. The midline, again, average temp. Amplitude is deviation, maximum deviation from the midline, or average temp from the midline, which is average temp. So basically what this tells us, oh, this is not temperature, we're talking about daylight, right? Which means it tells us the maximum amount of daylight and minimum, right, if you go all the way. And the period is how long it takes to get to back to where we started, which is basically number of months in a year. Right, the period is 360 divided by 30, which is 12. All right, another thing we want to be able to do is scientists try to determine if there's a relationship between the average daylight hours and the average temperature in Jacksonville. So average daylight hours and average temperature in Jacksonville. Trying to see if there's a relationship here. So we're going to start by creating a scatter plot. Let me put that into my calculator. Just to show you if you haven't figured this out, if you want to clear a whole list, you want to go up to the list itself, press clear, and then press enter, and it clears all the values, so you'll do them one by one. Okay, so I put the numbers in here. We're going to try to graph our scatter plot, which means, again, we need to go to this window and choose what we want our window to be. So we're going to look at temperature. This is what I graphed on the x-axis. The lowest it gets looks like it's 40 something, so let's just go ahead and put in 30 for the low. The highest it gets is going to be, looks like 80, 90. Let's put in 100. These ones are in degrees Fahrenheit, right? You can see that here, degrees Fahrenheit. And then for average daylight, again, let's go from 0 to 24, just because that's the maximum possible you could have. Graph these and you see our scatter plot. I need to go delete the functions that I have in there so you don't get this squiggly line. We're trying to find and interpret Pearson's R value, right? So what is the correlation coefficient? I'm going to go and delete these guys first so they're not on here. Come on. Okay, so Pearson's correlation coefficient assumes that it's linear, which you can see from the graph. It looks decently linear. Again, I need to get rid of these. But it assumes linear. And so what we're going to do is we're going to go stat. Oh, I get back to my home screen. Stat, calculate linear regression. Make sure you're using list 1 and list 2, just in case those have changed. Go down to calculate, and you can see our R value here is 0.881, right? So in this case, the Pearson's value is 0.881, which says there's, strong positive correlation. As temperature increases, so does the average daylight. And really, I'd probably put these the other way around, is like average daylight causes temperature. So if I would have thought about it better, my average daylight hours should be my x value, my independent variable. Okay, Spearman's rank correlation coefficient requires that we rank each of these values. So let me actually try to put this in a better spot so it's not so messy. See if I can put this down here. What we need to do is rank these from lowest to highest, right? So you want to start looking at these are temps and these are hours of daylight, finding the lowest one and then ranking them to the highest one. So let me pause and do that. Okay, so if you rank these are the ranks you should get, right? This one down here got a rank of 1 because it's the lowest, and then this is 2 because it's the second lowest, 3 third lowest, on and so on and so forth. What you want to recognize is that if you ever have a tie, which I didn't have any ties here, but let's say like I had two numbers, 10 and 12, sorry, two numbers that were tied, right, the same number. And let's say I'd already done 1, 2, and 3, and so I was on 4, and I'm like, well, what do I assign 4? Do I assign 4 to this one, or do I assign 4 to that one? Well, the answer is you wouldn't assign 4 to either. What you would do is you would find the average of 4 and 5, right, because these would be ranked 4 and 5, so that's 4.5, and they would both get a rank of 4.5 if there's a tie, right? Again, part of the reason I'm putting this in here is so you can practice using Pearson's, because you need to know how to do that, right? And so in my calculator, I'm actually going to go to my list. I'm gonna go, so I don't have to lose all this stuff. I'm gonna go to these lists. I'm gonna put in the list exactly as they appear here, right? So 2, 3, 4, 6, 8, 10, 11, 12, 9, 7, 5, 1. And then I'm gonna go to my list 4. I'm going to put it in exactly as it appears. And what I'm going to do now is to find Spearman rank correlation coefficient, I go to stat calc linear regression, except I perform a linear regression on those ranks. So in this case, I put those under list 3 and list 4. And so I'm going to go down and calculate it for that. And I get an R value for Pearson, Spearman's rank correlation coefficient is 0.8867. Right, so it just said find interpret, so this means there is strong positive correlation, whereas Pearson's meant there was strong positive linear correlation. Which one should I use in this case? Well, again, Pearson's is for linear, Spearman is for non-linear, and so these look very linear, right? They look aligned, therefore I should use Pearson, right? If I had a curve of dots, maybe something like this, then I should use Spearman. But I cannot use Spearman if it's monotone, if it's not monotone increasing, right? If it goes up and then comes back down, I cannot use Spearman's on this, right? Because Spearman's is only if it's always decreasing or always increasing, right? So don't ever use Spearman's on nonlinear like this. But any other nonlinear that always goes up or always goes down is fine. All right.